All right, welcome to the Explainer. Today, we are going to break down one of the most important data structures in all of computer science, the binary tree. Now, you probably don't see them, but trust me, they are the hidden backbone behind so many things you use every single day. We're about to find out how they work. We usually think about data in a straight line, right? Like a to-do list or the contacts in your phone, one thing after another. But the real world, it's rarely that simple. It's full of all these branching relationships, kind of like a family tree or a company's org chart. And for that kind of hierarchical data, a simple list just doesn't cut it. We need something that can handle all those branches. So here's our game plan for today. We'll kick things off by seeing why we need to move beyond simple lines. Then we'll learn the language of trees, get to know the special binary tree, and uncover the superpower of something called a binary search tree. And finally, we'll see where these things actually pop up in the real world. Okay, first up, moving from lines to hierarchies. The real problem we're trying to solve here is how to efficiently manage complex nested relationships. A simple list can't show you that one thing belongs inside of another. But a tree? Well, a tree is built for exactly that. Next stop, the anatomy of a tree. To really get how trees work, we need to speak their language. So let's get the core vocabulary down. It's pretty straightforward, I promise. Take a look at this. This diagram is going to be our map for the next few minutes. It shows the essential anatomy of a tree, and we're going to break down all the key terms you see here, starting right at the very top. Every single tree has to start somewhere, right? And that single starting point is called the root. You can see it right there at the top, node A. Think of it as the ancestor from which every other part of the tree comes from. Now let's talk about the most fundamental relationship in any tree, the parent and child. It's simple. A parent node has connections, or edges, that lead down to other nodes. Those nodes just below it, those are its children. So right here, B is the parent and D and E are its children. This simple connection is what creates all the branches. So what happens when a branch ends? Well, a node that has no children at all is called a leaf. Makes sense, right? These are the endpoints of the tree. If you follow any path from the top all the way down, you are always going to end up at a leaf. So how do we measure how big a tree is? Well, one of the key ways is its height. The height is just the number of steps or edges on the longest possible path you can take from the root all the way down to the most distant leaf. For this tree, that longest path has 4 steps, so its height is 4. All right, so we've got the general lingo down. Now, let's narrow our focus to a very specific and very important type of tree. It is time to meet the binary tree. What makes a binary tree binary? It's this one simple core rule. Every node can have at most 2 children. It can have a left child and a right child. It can have 0 children, that's fine. It can have 1, but it can never, ever have more than 2. That's it. That's the whole rule. Okay, now we're going to take it one step further. If a binary tree is special, then the binary search tree, or BST, is basically a superhero. It takes that 2-child rule and adds one more property that gives it an absolutely incredible superpower for finding things. And here it is. This is that superpower, the ordering property. It's beautiful. For any node you pick, all the values in its left branch have to be smaller, and all the values in its right branch have to be larger. This simple, elegant rule is what makes searching a BST so incredibly fast. Let's see this rule in action. On the left, you've got a valid binary search tree. Every single node follows that smaller, larger rule. But look at the right. That tree's broken. See that circled node? A value that's supposed to be in the larger right branch got stuck in the smaller left branch, and that one mistake invalidates the entire structure. Let's test this out. Look at the tree on the bottom left. The root is 6. Its left child is 3. Is 3 smaller than 6? Yep, we're good so far. But follow that same left branch down, and you hit a 7. Uh-oh. A 7 is larger than the root of 6, so it has no business being in the left subtree at all. That one violation makes the whole thing an invalid BST. If you check the others, you'll see the ones on the top left and bottom right are perfectly valid. So why does that ordering rule matter so much? Because it gives us a lightning-fast way to find anything. You just start at the root and ask a simple question. Is the number I'm looking for smaller or larger than this node? If it's smaller, you go left. Larger, you go right. At every single step, you get to completely ignore half the tree. This lets you zero in on what you're looking for incredibly quickly. Okay, I know this has all been a little bit abstract, so let's bring it back to the real world and see where these trees show up on your computer screen every single day. And this is the perfect example. Your computer's file system. That main drive, the C drive, or your root folder, that's the root of a massive tree. Every folder is a parent node, and the files and other folders inside it are its children. You navigate this tree every single time you click around looking for a file. And this quote from our source material just says it all. The reason you can have hundreds of thousands of files on your computer and still find the one you want in seconds is because of this efficient hierarchical tree structure. It's literally built for quick retrieval and for easy expansion. Now let's peek behind the curtain for a second. This is the output from a program that built a binary search tree. Now there's a special way to read a tree called an in-order traversal, which basically reads everything from the smallest value to the largest. And look at that first line of numbers. It's perfectly sorted. That's the proof that the ordering property is working exactly like it's supposed to. The text below that just gives you a little glimpse of the tree structure the computer built to make that happen. So, what are the big takeaways from all this? First, trees are all about modeling those hierarchical relationships. Second, binary trees are the special type with that strict two-child limit. Third, binary search trees add that magic ordering rule for super fast searching. And finally, this isn't just theory. These things are the backbone of systems you use constantly. When you really stop and think about it, these tree structures are everywhere, organizing our digital lives. They organize your files, they help databases find information, and they even help structure how data flows across the entire internet. So I'll just leave you with this question to think about. What's the most complex tree you have to navigate in your day-to-day life? Thanks for watching.